Hello everyone, I'm Tim Heegman and I'm a PhD student at the Vrije Universiteit Amsterdam. Today I want to share with you our work on Grade10, a framework for performance characterization of distributed graph processing application. Before I get into the how, let me tell you why we should care about distributed graph processing applications or their performance. Graphs are ubiquitous in our modern digital society. Graphs are used to analyze our interactions on social media, to represent physical infrastructure such as road or energy networks, and to model the natural world through brain networks or protein interaction networks in bioinformatics. In short, graphs let us study collections of entities such as people, road junctions or neurons, and their relationships or interactions. In practice, graphs can be very large. Estimates for some of the largest known graphs that exist today include billions to tens of billions of vertices in a social network or web graph, and up to a few trillion edges. The network formed by neurons and synapses in the human brain is several orders of magnitude larger still, on the order of 100 trillion connections. In addition, vertices and edges can have many attributes, such as the name and other personal information of each user, or for each relationship, when it was established, the nature of the relationship, and so on. All in all, large graphs can be terabytes or even petabytes in size. Due to the large data volumes and the random data access patterns inherent in analyzing graphs, distributed processing is a natural choice. I do want to point out that although it may seem from these examples that large-scale graphs are reserved for giant corporations, this is not true. According to a 2017 survey by Sao et al., graphs with billions of edges and terabytes of data can be found across multiple domains and in organizations ranging from very small to very large. Therefore, large-scale distributed graph processing is of interest to many, and not just the Googles and Facebooks of the world. To address the need for graph processing, both academia and industry have developed numerous graph processing platforms. A user may implement their graph processing application on top of one of these platforms, thereby benefiting from the distributed processing pipeline implemented and optimized by the platform's developers. However, previous work has demonstrated that the performance of graph processing applications is highly sensitive to not only the selected platform, but also to the structure and values of the input graph and to the selected graph algorithms. For the community to build better platforms and for users to correctly tune the platforms they use, we believe that understanding graph processing performance is critical. Therefore, we ask in this work the question: how to characterize the performance of distributed graph processing applications. Performance characterization for distributed graph processing is daunting due to three key challenges. First, graph workloads are irregular and dynamic. The operation of a graph workload depends not only on the size of the input graph, but also on the graph's values. For example, a breadth-first traversal on a well-connected graph with low diameter behaves very differently from a traversal on a graph with long chains and high diameter. Therefore, modeling-based approaches are unlikely to capture the full complexity of graph processing performance, and a more empirical approach is needed. Second, there is a semantic gap between system-level and workload-level monitoring data required for performance characterization. Typical cluster monitoring tools may reveal when an application's execution was CPU or network bound. However, these tools cannot relate system-level bottlenecks to workload-level concepts like iteration boundaries or workload skew. Third, there's a trade-off between the accuracy of collected performance data and monitoring overhead. Due to the irregularity of graph workloads and the typical architecture of distributed graph processing platforms, performance bottlenecks can shift rapidly. Therefore, a monitoring approach that can capture performance data at fine granularity while maintaining low overhead is desired. To address these challenges, we propose Grade10, a framework for performance characterization of distributed graph processing applications. So what does performance characterization using Grade10 look like? In short, Grade10 collects performance information from the execution of a particular graph application and analyzes this information to identify bottlenecks and other performance issues. Grade10's performance characterization process can be split into 4 key steps. The first step is data collection. Grade10 extracts an execution trace and a resource trace from log files and system monitoring data. These traces capture a timeline of the operations the application was performing and how much of each resource was used in the process. I will explain execution traces in more detail on the next slide. The second step is resource attribution. Grade10 combines the execution and resource traces to attribute the observed usage of resources over time to individual operations in the graph application's execution. In the third step, Grade10 uses the resource usage attribute to each operation to determine which resources an operation was bottlenecked on and when. Finally, in the fourth step, Grade10 identifies performance issues such as high-impact bottlenecks and workload imbalance. It estimates the impact of performance issues on the total runtime of the graph application by replaying the execution trace in simulation under specific what-if scenarios. For example, what if the network was infinitely fast and there were no network bottlenecks? I do not have time to exhaustively explain every aspect of this process, so I will highlight several elements. Please refer to our paper for more details. A Grade10 execution trace is a hierarchical representation of the operations performed during one particular execution of a graph application. Depicted on the right is an example trace. At the top is an operation called app, which represents the entire graph application. This operation can be divided into three sub-operations: load, followed by process, and finally store. The process operation in turn can be split into supersteps, which is a common name for iterations in distributed graph processing, and so on. For each operation in the execution trace, Grade10 records the start and end time of the operation, as well as any dependencies that may exist between operations. These traces can be made arbitrarily deep and detailed to support more fine-grained performance analysis. In practice, the smallest operations we recorded in our execution traces were compute tasks which take on the order of tens of milliseconds to tens of seconds. These can be recorded without discernible performance overhead. This whole process is guided by an expert user, ideally a developer of the graph processing platform, who provides a model describing the kinds of operations an application running on their platform is expected to perform. The expert user also adds some additional logging where needed to record when those operations occur. This only needs to be done once for a given platform, and the resulting model can be reused to analyze the performance of many graph applications. In the resource attribution process, Grade10 combines an execution trace with coarse-grained resource monitoring data. It infers for each operation in a graph application how many resources the operation used over time. Details are available in the paper, but in this presentation I want to share an intuition for how and why it works. First, consider the figure on the left, which depicts the utilization of a resource, say a CPU, by some imaginary graph application. The horizontal axis represents time, and the vertical axis represents the utilization of the resource between 0 and 100%. The shaded areas in three different colors correspond to three different operations in our graph application, and each area depicts how much a particular operation contributed to the total utilization of our resource. For example, the yellow shaded areas in the bottom left and bottom right indicate that the corresponding operation used about 15% CPU during those time intervals. The lack of yellow area in the middle time interval indicates that the yellow operation did not use the CPU during that period, perhaps because the red and blue operations were saturating the CPU at 100% and the yellow operation had the lower priority. If we were to monitor the utilization of this resource using run-of-the-mill system-level monitoring, we lose a lot of information. Monitoring tools measure the average utilization over coarse time periods, so they miss short-term variations in utilization. Also, monitoring tools do not have information on our application's internal operations, so they only measure the total utilization of our application. Because the figure on the left tells us much more about how our application is behaving, we ask the question, can we recover some of the information we lose through monitoring? We do this through a process called resource attribution. The input of Grade10's resource attribution process consists of the coarse-grained resource traces obtained through monitoring and an execution trace. The intuition behind this process is that there is a strong correlation between the kinds or amounts of resources consumed by an application and the kinds of operation that application is performing at any given moment. For example, CPU utilization should be much higher when lots of compute threads are active than when the application is waiting at the synchronization barrier. Therefore, we can use the fine-grained execution trace to estimate an application's demand for a resource over time, and combine this with the coarse-grained resource trace to estimate how a resource was utilized over time. First, Grade10 estimates resource demand by considering for each operation in the execution trace when it was active and how much of a resource the operation is expected to use. This process is currently expert guided, so an expert can use a simple set of rules to indicate whether demand for a resource is known, such as 1 CPU core per compute thread, unknown, or even non-existent, such as a compute thread that's known not to use any disk or network resources. The resource demand curves are used to upsample the collected resource trace, effectively shaping the resource utilization curve to match the estimated demand. Finally, the upsampled resource usage is attributed to individual operations in the graph application according to the relative demand of each operation. Overall, we found that using this process, Grade10 is able to find a good approximation of the true resource utilization of a graph application using its resource attribution process, with an error of under 20% when upsampling by 8 times for our tested platforms. Now that I have told you what Grade10 is and how it works, I want to present our experiments in which we used Grade10 to characterize the performance of a set of graph processing jobs. We used in our experiments 2 different graph processing platforms, Apache Giraph, which is implemented in Java, and Powergraph, which is implemented in C++. On both platforms, we execute 4 algorithms and 2 data sets selected from the Graphalytics benchmark. All experiments were performed on 10 common off-the-shelf machines in a local cluster. In our first experiment, we investigate the impact of different bottlenecks on the processing time of an application, as estimated by Grade10. The impact computed by Grade10 is an optimistic estimate. That is, it indicates by how much an application could be sped up if a bottleneck were eliminated entirely and the rest of the application remained unchanged. In practice, performance optimizations may only reduce and not eliminate a bottleneck, or they may introduce new bottlenecks by trading off the use of one resource for another. Think, for example, of the CPU network trade-off when applying compression to network traffic. Depicted in this figure are the top bottlenecks for an application running the breadth-first search algorithm on the DataGen 1000 graph using the Giraph platform. Each bar in the figure represents a different resource. The height of each bar indicates the total impact of bottlenecks on the corresponding resource as a percentage of the graph application's processing time. From left to right, the bottlenecks analyzed for this experiment are CPU bottlenecks, garbage collection or GC bottlenecks, and message queue bottlenecks. We define a garbage collection bottleneck as a period during which application execution is halted while waiting for Java's garbage collection to complete. A message queue bottleneck is a period during which Giraph's compute threads are halted because Giraph's internal message queue is full. Not depicted in this figure are network bottlenecks because they have an impact of less than 0.1% in all Giraph workloads. For this particular application, Grade10 finds that message queue bottlenecks are most impactful at around 19%. Overall, this application spends the majority of its time not bottlenecked on any resource, which may be indicative of high runtime overheads, such as long pauses during synchronization barriers. Expanding the figure to include more algorithms, we find that for all applications using Giraph on the DataGen graph, message queue bottlenecks are the most impactful, followed by garbage collection and finally CPU. In particular, Grade10 finds for 3 of 4 applications that eliminating message queue bottlenecks could reduce processing times by over 50%. Finally, for the 4 applications using the Graph 526 dataset, we observe similar results, with exception of the community detection or CDLP algorithm, Message queue bottlenecks are most dominant and the impact of CPU bottlenecks is limited. Overall, our findings match earlier observations by Satish et al. In 2014, who found that Giraph consistently fails to saturate CPU and network resources, but achieves significant performance improvements by tuning Giraph's communication subsystem. We repeat the experiment on Powergraph with the same workloads. Note that for Powergraph the depicted resources are different. Powergraph does not use a garbage collector like Giraph does, nor does it use a message queue that can lead to bottlenecks like Giraph. Instead, some Powergraph jobs are bottlenecked on inbound and outbound network traffic, depicted by the middle and right bar in each group of 3 respectively. In contrast to Giraph, Grade10 finds that our graph applications running on Powergraph are primarily CPU bound, though the impact of CPU bottlenecks varies significantly across the selected graph algorithms. Overall, we have shown that Grade10 can be used to identify resource bottlenecks, which vary significantly across platforms, algorithms, and datasets. As our final experiment, we investigate the impact of workload imbalance on the execution of Powergraph jobs. Without going into too much detail, Powergraph distributes the workload of an application by assigning part of the input graph to each of its worker machines. On each machine, a set of compute threads concurrently process small pieces of the graph until they have collectively processed the part of the graph assigned to their machine. Due to the irregularity of graph workloads, some machines and some threads will have more work to do than others in a given step of a graph algorithm, so imbalance in the execution times of compute thread occurs. We used Grade10 to identify performance issues arising from workload imbalance by asking the question, what if the workload of compute threads in Powergraph was perfectly balanced? In other words, what if all compute threads took the same amount of time to complete while still performing the same total amount of work? In our paper, we present several findings from this experiment, but for the presentation I want to highlight one that led to the discovery of a synchronization bug. Grade10 pointed out that workload imbalance in jobs using the community detection algorithm accounts for over 40% of total processing time. Most of this overhead was concentrated in one step of each job, so we manually inspected that one step in more detail to find the root cause. Depicted in this figure are the durations of all compute threads in one particular step of a Powergraph job. The horizontal axis lists the 10 workers used by this particular Powergraph job. Depicted vertically are the thread durations for all threads on a given worker. Note that the thick lines are in fact tiny box plots. Overall, this figure matches our expectations. On most workers, compute threads are well balanced thanks to Powergraph's work stealing mechanism. Between workers, thread durations are imbalanced due to Powergraph's static partitioning and the irregular nature of graph workloads. However, there are a few notable outliers. In particular, on worker 6, the slowest compute thread takes nearly 3 times as long as the average thread on that worker. If we were to eliminate the outliers on workers 6 and 7 through better workload balancing within workers, this step in the graph application would only take as long as the slowest worker, in this case worker 4. This would result in a reduction of 58% in the duration of this step. We were ultimately able to find a race condition in Powergraph's handling of thread synchronization that caused this phenomenon. More on this in our paper. In short, we used Grade10 to identify a performance bug in Powergraph related to workload imbalance. In conclusion, we have shown how Grade10 collects and combines execution and resource traces to create a fine-grained view of a graph application's performance through a process called resource attribution. We have shown that performance bottlenecks vary greatly across graph processing platforms, algorithms, and datasets, thereby confirming the need for comprehensive performance characterization in distributed graph processing, as provided by Grade10. And we identified using Grade10's performance issue identification process a previously undiscovered and spurious synchronization bug in Powergraph. Thank you for watching.